Okay, in this section we're going to be looking at the principle of superposition. Superposition and circuit analysis. Now, you may have run across this principle of superposition before. You might not have, depending on whether you've taken QEA or not. But basically, this is taken by some people to be the defining principle for linear systems. And linear circuits are types of linear systems. And so the basic idea is, if I have a linear system, and suppose I know that if I put one input into it, I get a certain response. I get, say, y1 for x1. And I have the same linear system, and I put in some other signal x2. I'm going to wind up getting some other response, say y2. If the system is linear, then if I put in some combination, some linear combination of x1 and x2, say c1 x1 plus c2 x2, what I get out is that same linear combination of y1 and y2. I get c1 y1 plus c2 y2. Of course, C1 and C2 here are just constants, so I could make them each 1. And if I were to put in the sum of the two signals, I just get the sum of the two individual responses. So basically what the principle of superposition says is that the response of a linear system to some summation of signals is equal to the response, or the summation of the responses of the system to each of those signals independently. And the cache value of that in terms of circuit analysis is really, it gives us a way of dividing and conquering. So it's a divide and conquer technique for circuit analysis problems. So we can take what seems like a fairly complicated problem and break it up into simpler problems, and the answer is just given by superposing the results of the independent subproblems. So that's a very easy thing to remember how to do, and it turns out to be a very important tool to put in our toolbox. So what does this look like? So we're going to start out with a fairly simple example. And in order to apply superposition, you really need more than one source, more than one input to the system. And the idea is that you turn off all the other ones except for one. You consider the response of the circuit due to that first source, and then you march down all of the sources in turn, and you turn each of them on in turn, consider the response of the system to each independent source, and then you just superpose the pieces to get the overall response. So we're going to do a simple example, which is our voltage divider, okay, with a bit of a twist. So here we have our input voltage source, Vn. We have R1 and R2, and we're interested in the voltage across R2, which is V out. And normally, this is all we have for a voltage divider. But what we're going to do is we're going to connect a current source, which is our second input, if you like, to the output here, and we're going to inject some current I out into the output node, and we want to know what is V out as a function both of V in and I out. Now this is going to be a simple enough problem that we can actually solve the system considering both inputs applied simultaneously, and then we're going to use superposition and compare the two. And it's not necessarily going to be apparent why this is necessarily any advantage to us, but I think we'll do a more interesting example in the next segment that I think will illustrate why this is a useful thing. May become apparent even now, but so the first thing we're going to do is apply Kirchhoff's current law to solve the whole thing together. We're going to apply Kirchhoff's current law at this node here, okay, at the output node. And so KCL, I feel like this is sort of a one-node nodal analysis. So we don't have a matrix, but we just have a single KCL equation. So the current flowing through R1, call I1. Let's say the current flowing through R2 is I2. We have KCL at the output node saying that the sum of the currents flowing in, I1 plus I out, is equal to I2. And we can express I1 in terms of V in and V out as V in minus V out over R1, so this is I1, plus I out is equal to I2, which is just V out minus 0, we call this ground, over R2. This is I2. And now we just want to solve for V out. So we can move this V out over R1 to the other side of the equation, flip the equation around, factor the V out out, and we get V out times 1 over R1 plus 1 over R2 is equal to what's left over on the left-hand side. We get V in over R1. It's from this term here, plus I out. And of course, we could recognize this, if we were astute, as 1 over the parallel combination of R1 parallel R2. Right, because the parallel operator is defined to be the reciprocal of the sum of the reciprocals, and so we get the sum of the reciprocals of R1 and R2, so that's just 1 over R1 parallel R2. And so we can multiply both sides by R1 parallel R2 to get rid of it on the left-hand side, and isolate V out as R1 parallel R2 over R1 times V in plus R1 parallel R2 times I out. Didn't leave myself enough room there. Could fix that. Okay, and we could take this a step further if we like. If we take R1 parallel R2 and expand it out as the product over the sum, we'd have an R1 R2 upstairs over R1 plus R2, and that R1 would cancel this R1 down in the denominator. And that leaves us with a slightly more satisfying result, which is R2 over R1 plus R2 times Vn plus R1 parallel R2 times I out. Okay, so V out is given by the sum of two things. We have the familiar voltage divider ratio that we're used to, times V in, plus a term due to I out, which is given by R1 parallel R2 times I out. Okay, that was fairly simple. We had to be a little clever to get the answer in this form. You'll notice we had to, at this stage down here, recognize 1 over R1 plus 1 over R2 as 1 over R1 parallel R2. I mean, we could have done something like put this over a common denominator by multiplying this one by R2 over R2 and this one by R1 over R1, and we'd have R1 plus, or R2 plus R1 over R1 R2, and then we could have multiplied through by the reciprocal of that, and that would have immediately given us basically our R1 R2 over R1 plus R2 here times V in. We could have canceled the R1 and gotten our voltage divider ratio. But then we'd have to recognize that R1 R2 over R1 plus R2 is R1 parallel R2 to put it in this form. Okay, so we could have maybe saved ourselves the step of collapsing this and then expanding it back out here, but at the cost of having to recognize that this was the parallel combination of R1 and R2 there. So anyway, that's the sort of monolithic simultaneous solution of this problem. And now we want to go on to consider, what does the superposition approach look like? Okay, so we're going to erase some of these things that we put on here. Okay, so we're going to have two sources, so there'll be two components of V out. We'll number these sources 1 and 2, and V out is going to be given by V out 1 plus V out 2. So this is just the principle of superposition. It tells us that there's two sources. We're going to have a response V out due to the first source, and V out 2, which is the component of V out due to the second source, and we're going to consider these two sources independently, and this is the superposition of the two responses. And the way this works is we want to set the value, when we're considering the first source, we set the second source's value to 0. Okay? So how do we set the value of a current source to 0? Well, we talked about that. You remember a current source has, in the IV plane, a horizontal line as its IV plot, right? And if the value of the current source is 0 amps, that just means it's the horizontal axis. Well, we met another type of device that had that sort of IV curve, and that was an open circuit. Okay, so to turn a current source off or set its value to 0, we can basically replace it with an open circuit. Okay, now we've removed that current source from injecting a current into the output node, and we've reduced our circuit with the two sources into our familiar typical voltage divider that we've now solved. And if we put that in our L1 cache, and we can bust it out when we need it, we can write down that V out 1 is just V in times R2 over R1 plus R2. No problem. And we're done with that one. And so the idea is then to go on to source 2, which in this case is our I out, which we can turn back on. And we want to turn off the first source. Okay, so how do we turn off a voltage source? We set its voltage to 0. And if you remember, the voltage source has an IV curve that basically looks like a vertical line at whatever the value of the source voltage is. And so if we set the value to 0, then the IV curve is just a vertical line that's on the y-axis. And we met another type of device that has an IV curve that looks like that, a vertical line, and that is the short circuit. Right? It's the limit of a resistor as the resistance goes to 0 or the slope goes to infinity, right? A vertical line. And so to turn off the input voltage source, we replace it with a short circuit. Which is just a little segment of wire. And now we're interested in what is the value of V out due to the input, or the current source I out. Well, this is an easy enough thing to see, because here we have, from the vantage point of our I out current source, we look in here, and actually we see R1 and R2 in parallel with each other. Now, from the input voltage source point of view, R1 and R2 were in series. But if we look from the point of view of looking into this middle node here, okay, we see two parallel pathways that current can flow. The current splits. Some of it goes through R2, some of it goes back through R1. And if we were to redraw this, we might take this end of R1 and just move it around here and flip R1 around, and we would see that R1 and R2 are actually, in fact, in parallel. And we can collapse those two resistors into a single equivalent resistor whose value is R1 parallel R2. And so V out 2 is just given by Ohm's law as I out times that equivalent resistance. I out times R1 parallel R2. And so we just substitute in to this original superposition equation to find that V out is equal to R2 over R1 plus R2 times V in plus R1 parallel R2 times I out. And with a little practice, we might even be able to kind of turn these sources off in our head without redrawing the circuit. And we might even be able to write down this answer in one step without having to write down these intermediate results. So I'm not saying that that should be something that you can do right off the bat, but it's certainly something that with a little bit of practice you can actually do. So notice when we wrote these down and we had the circuit kind of in its sort of sub-problem states with these various sources turned off in turn, these forms of the voltage divider ratio and the parallel combination of R1 and R2 were actually quite readily apparent by inspection of the circuit diagram in a way that it wasn't quite so obvious when we wrote our KCL equation down and we're kind of going through some algebraic steps. We had to actually put some mental effort into recognizing, for instance, that 1 over R1 plus 1 over R2 as the 1 over R1 parallel R2. And then to get back the voltage divider ratio, we had to expand out the R1 parallel R2 and divide by R1 to get the voltage divider ratio back. Whereas here it came out for free. And that's generally sort of a feature of this type of approach. So I like this example for a couple of reasons. One is it's a simple enough example that we can actually see very easily the two different approaches of solving the one KCL equation simultaneously for the two with the two sources applied at the same time. And also we can apply the superposition idea and get the same answer without too much algebraic angst to put the one into the form that's equivalent to the other. But this is actually quite a practical thing as well. We work with voltage dividers all the time, and it's a way of creating a reference voltage someplace from a power supply that may not have the value that we actually want. But all the time, we wind up sort of assuming no current flows out of the middle node. Right? That's the way the voltage divider is usually set up. But if we actually have some current that has to be supplied to some load that's connected to this middle node, the question is, how much does that current shift the voltage away from the desired value that we pick by whatever the total voltage is here times the voltage divider ratio? Well, the answer is it shifts precisely by the current that's being source or sunk from this middle node times R1 parallel R2. We would say the resistance seen looking back into this node here. And so if you need to supply milliamps of current, and you're building this resistive divider out of, say, kilo-ohm resistors, then milliamps of current times kilo-ohm resistors is like volt shifts, right? Because kilo times milli is basically 1, right? 10 to the third times 10 to the minus third is something that's on the order of 1. And so if I'm pulling out milliamps of current and I've got kilo-ohms of resistance here, that means I'm going to be shifting this voltage away from its desired value by like volts, which is quite a lot. In order to be shifting only by millivolts, if I had k-ohm resistors here, I would need to be drawing out microamps of current, which is 10 to the minus 6. And so very often we'll need to buffer this voltage divider so that the op-amp buffer would supply the current that is needed by whatever we're connecting this to, and we don't disturb the voltage on this middle node. A lot of times people forget that. Actually making a power supply that can supply current out of a resistive voltage divider is actually quite wasteful, because we have to either use such low resistors here in our voltage divider that we burn a lot of power to make this intermediate voltage stiff enough to be able to withstand sort of taking or putting in some reasonable amount of current. So there are much better ways of actually creating a voltage source, like a linear regulator or something like that, that is not super efficient, but at least we're not dumping power through this other resistor here, R2. We're only dissipating power in the stuff that's up here for the most part. Well, I think that's going to be it for this segment. We have one more example that I'd like to develop with superposition. It's going to take longer than I think is warranted by one video. So that's going to be it for this one, and we'll see you next time.